again. Good. All right. Let me just. So this is really the third part of the tutorial, and in fact, this has two bits. These are two bits covering techniques that we care about, or at least we have decided to focus on in the interest of the tutorial. And then I will talk about, some perspectives on the area. Okay, I'll first start off with perhaps what is easiest to grasp for most people, both from the technical and the non-technical landscape, which is the approach of counterfactuals. Okay. Now, if you haven't heard them, counterfactuals have been very interesting for many, many disciplines, going back to philosophy, certainly cognitive science. And in machine learning, at least, counterfactuals have now become a way to explain local decisions by considering, in quotes, other possible ones. And we'll see what that means, okay? So what it is if you think about a prediction, right, you might think about two things. You have a certain data point, and let's say this data point has been accepted or rejected, and you're looking for what would it take for the decision to be flipped, right? So if it was accepted, I want it now to be rejected. And if it was rejected, I now want it to be accepted. What would it take, right? And similarly, if you're looking at the probability of some prediction, and you're saying, okay, the probability of this image being a dog is 40%. What would it take for it to be 50% or 60%, right? So what you're looking for is this idea of a closest possible world, because you don't want the explanation to be something diametrically opposite. You want it something to be close, but changed in small ways such that they make sensible and you can understand the delta between the explanation and the data point at hand, okay? And this is what now constitutes as counterfactual explanations. If you think back about the narrative we had with Jane, the data scientist, if you remember, the stakeholder was asking about this individual, Mr. X, and Jane was saying that if you decrease the income of this individual by 50%, then it would be rejected. If it was only decreased by 25%, it would be accepted, right? So this is a kind of explanation you're looking for. So this brings us to the question about what makes a good counterfactual, right? And there are a bunch of different criteria you can think about. The first thing you want to think about is that you want an explanation that is closest to the desired target output. So for instance, if it was a dog by 40%, you're perhaps looking to find that it's a dog by 50%, okay? So you want to look at that kind of explanation that's closest to the desired target output. You want it to be also close to the original data point, right? As I said, you don't want a data point that looks completely different. And so you're left, again, not really understanding what it is about the data point that's making it a yes or a no or an accept or a reject, right? So you wanted something close to the original instance. You want to minimize, so in fact, this goes hand in hand with the idea that you want to minimize the number of features change, right? And you also want likely features, right? You don't want to say the only way this person would get the loan approved is if we swap the gender or something like that, which wouldn't really be feasible. So you want explanations that are very close, okay, to the actual data point you care about. So this can, in fact, be converted to a kind of formulae. And it looks like a bit like this, okay? So again, I'm not going to go into too much technical details, but it's just to give you a flavor of what it looks like in practice, okay? So let's imagine here that X star is the data point that we initially started off with. And the explanation that we're looking for is this X, okay? So you want to minimize X such that the following 4 criteria is satisfied, okay? Let's start from right to left, okay? If you think about the 4th criteria here, it was to look for statistically likely features. So what you're saying is, I want the explanation to be fairly close to my input data, right? I want it to match and mirror the input data. And I don't want it to be arbitrarily different, right? I don't want it to suggest values that don't make sense, right? So that's what the 4th criteria is. The second criteria is that you want to minimize the number of features changed, okay? So this is O3 in this equation. And this is usually captured by some kind of decision function, okay? So not decision, sorry, distance function. It's trying to say, how do I change it minimally such that this is part of the explanation? The second one is saying that it's as close in value. Again, you use some kind of distance function, and this is O2. And finally, it's saying it's close to the desired target output, which means that if you look at the trained model, which is F hat, when you input the explanation data point to the trained model, it is as close as possible to the desired outcome. So the desired outcome could also be binary, right? So in which case this is a yes or no. Is it the case that the trained model on the explanation is exactly matching the desired outcome, or it's not matching? Right? So this is a way you can construct an optimization function basically to get a counterfactual explanation, okay? This is one approach. There are others, and I'll consider one other. But in the meantime, here are some open questions for us to reflect on. So, if you're looking at the second question, for instance, the closest possible world is another way of saying the least amount of changes, right? You don't want the changes to be arbitrarily large. You don't want a data point that's at the other end of the spectrum. You want something that's close, and so that constitutes as your counterfactual explanation, okay? So here's another way of generating counterfactuals, and this also is kind of easy to read, at least at a first glance, okay? So what is this saying? It's saying that my desired explanation is X prime, okay? My input data point is Xi. So it's saying find me an X prime such that I'm minimizing the distance between Xi and X prime. So it's minimizing the distance between the explanation and the data point that I initially gave it. But I also want to minimize the difference between the expected output. So the output that the trained model gives for my explanation, that's f of X prime, and the desired output, that's Y prime. Okay, so it's basically saying, let's assume my data point is Xi, and I want to come up with an explanation that's telling me how to get the loan rejected, because the output for Xi, it's accepted. Okay, so what would it take for Xi to get rejected? And the explanation here is X prime, such that X prime is not too far off from Xi, right? And nonetheless, its label is flipped. Okay, so that's essentially the idea. So it's, I guess, a simpler way of looking at the counterfactual criteria. And this has become a very popular definition for counterfactuals at the moment, okay, because of its simplicity. The distance function, again, is important, but I won't go into how exactly that's calculated. But I hope you get the general idea. But if it's not clear, feel free to, raise your hand or write in the chat about what the question is, okay? Let's, in the interest of, let's say, exhaustiveness, let's look at one cute application of counterfactuals, okay? Now, let's say you have, if you're looking at the bottom box, right? Let's say you're looking at a certain kind of bird, and you're trying to understand what would constitute as an explanation for the label of this bird to be something else. So what the approach of the algorithm does is that it finds what is called as a distractor image. So it finds an image I prime such that the label for this is C prime, okay? It calculates the difference between I prime and the original image I, and it creates a composite image where this the delta is applied to the original image. Okay, so in a way, it has told you what needs to change in the original image such that it gets a different label. So this is one of the applications of counterfactuals in a visual setting. So to take a stock of it all, what are the advantages of counterfactuals? It has a very clear interpretation. I mean, my guess is that even if you're not familiar with machine learning, it should be fairly easy to grasp how counterfactuals intuitively work, right? There are really two options in terms of results, right? On the one hand, it's providing an actionable change. It's telling you what needs to change for the decision to flip. And it's also telling you that the counterfactual itself is an interpretation, right? It's telling you what the closest data point looks like for a changed label. It's model agnostic, so it's very easy to apply to a whole range of machine learning models, and they turn out to be applicable in areas outside machine learning as well, okay? And they are somewhat easy to implement when you compare it to other techniques. So all of this is great. It does come with some complications, however. As you might have guessed, it is hard to define what is the best or the true counterfactual, as you could have multiple possible suggestions about what to change to get the output. So it's up to the user to really kind of navigate this and figure out what works for them. Okay, and sometimes counterfactuals can also contradict the suggestion. So one counterfactual might be suggesting that by improving this income, you might get the loan approved. Another counterfactual might be saying just by keeping the income the same but dropping all the other commitments, you could get the loan approved. So one way or another, you are often left with different actionable properties, which might be, kind of challenging to navigate for a layperson, right? So a data scientist needs to somehow convert these insights into one choice point for the user, or one or more choice points, but needs to explain how these work, right? So there can be some intricacies in understanding counterfactual explanations. And of course, the last point is, as I said, because they try to operate within the region of the data point, they are local, and this means that you could perhaps misunderstand a global aspect of the model by focusing purely on the local aspects, right? So there might be global behavior that is in some sense contradictory to the suggestions offered by the local behavior. So, there are these issues to grapple with, okay? Let's stop for a few open questions here. I'll let you read them at your own time. The last question in particular is a kind of homework question, if you will, just to try things out, to imagine what counterfactuals might look like for multi-class classification. But the second one is interesting, right? How counterfactuals help aid a machine learning user and the end user. The difference is that often machine learning researcher might be making sure that the decision boundary is behaving in a sensible fashion, that it's not randomly flipping decisions based on small changes, right? Whereas the end user might say, oh, what is getting the loan approved for me or rejected for me, and what would I need to change, right, to get myself approved? So it could be the same counterfactual explanation that applies to both cases, but they have slightly different use cases, right? Slightly different purposes depending on the context. So this is something that, this is another reason I think counterfactuals are very important and popular, because they do have this flavor of being useful both to data scientists as well as end users, okay? Is that all making sense? I'll, as I said, feel free to chat, but otherwise I'll move on to the next technique. It looks like I might still have time to very quickly cover the next technique as well. It's anyway not too much detail. It's just an overview. Just to see another technique that's kind of useful and to provide some more detail are deletion diagnostics. If you remember, deletion diagnostics referred to this aspect of the interaction between the stakeholder and Jane, where she was saying, suppose I have inaccurate data about Mr. X. what would it look like, with respect to the decision boundary if you removed him? And Jane says that the decision boundary is fine to even remove Mr. X, right? But it can happen that if Mr. X is really representative, then the decision boundary could drastically change by removing him. And this should kind of give you a hint how this works, right? Basically, the idea is to find representative data points that tell you how the model is working, okay? And they form, they really are a class of techniques called as robust statistics, because they're trying to approximate the model retraining and trying to construct the function where they're basically trying to describe the model as a function of the data, which we all know machine learning models to be, right? We all understand that there's the algorithm, but the actual model deployed is a function of the data, and deletion diagnostics are highlighting this function and trying to provide some clarity on how the model behaves based on certain data points, okay? So the way it works is, as you would expect it, you basically retrain the model with that data point removed and try to understand how the decision boundary works, okay? So, so essentially, the way to think of this is that you have certain data points which you could consider to be influential instances. So these are instances that are clearly deciding and contributing to how the model behaves. And in some ways, they are also a global explanation, right? Because they are telling you the entire boundary of the model is crucially dependent on this one instance. So there are examples of explanation by example. There are examples of global explanations to a large extent. There are examples of potentially simplification, right? Because if you can provide a model that is purely based on the influential instances, then you have a nice description of what the model is doing. And indeed, the dimensions of deletion diagnostics are as follows. For instance, they help you explain the model by pointing out what the critical data points are. If you just collect the most critical data points, then it provides, in fact, a more effective scheme for training your model. Because you have a smaller set of data points, right? And how they work is, as you would expect, you delete the instance, retrain the model, you observe the change, and that's basically it, right? Now, this is a very naive and brute force technique for doing deletion diagnostics. I should point out that there are cleverer schemes that are based on, for certain parameterized models, but I won't go into them here. It suffices to say that this naive approach is, it gives you a good idea for how exactly deletion diagnostics work, okay? So, I let you reflect on the questions here, but perhaps one question we can tackle is the third one in terms of how deletion diagnostics helps with model debugging. And the answer here is that because you are trying to understand what the model might have done improperly, you're basically identifying the most critical instances and seeing whether the labels that you provide to these instances is reflective of how the model is supposed to behave. And if you find problems in these instances, then you can go back and analyze what the model is doing, what the model is doing incorrectly, right? So they are extremely useful for model debugging. To wrap things up, I mean, the advantages here are that they're model agnostic, as I said, at least a brute force technique you can do on any model, right? It is fairly generalizable because you don't really need to, I mean, in a way, any sort of machine learning model, and you want to ask this kind of counterfactual statement as to what happens when I delete one data point, this deletion diagnostics comes to the rescue, right? So it applies to any architecture, any machine learning model. It's a kind of solution to look at the robustness and the sensitivity of the decision boundary for all machine learning models. As I argued, it is useful for debugging and potentially model comparison. but this should give you a hint as to what the disadvantages are. Clearly, it is expensive. Retraining a model is challenging, and it takes a lot of compute time. And clearly, if you want to take the brute force approach, it's not great, right? There is also this kind of arbitrary aspect to understanding inferential instances in terms of what exactly contributes as influential in a kind of numbers, right? Is it 20 data points? Is it 40? Is it 5, right? There is some kind of arbitrary aspects to it that is hard to define or hard to quantify in a global way, okay? So that's essentially deletion diagnostics for you. I'll leave some open questions. As I said, there are some clever ways of doing deletion diagnostics, and this corresponds to the first open question we have here. The second one is also a kind of homework question, if you will, to see how they could be applied for random forest. I mean, there is a naive brute force way of doing it, right? You retrain the random forest by removing the data point, but that's too expensive. The question is if there's a smarter way of doing that. And again, the third data point is something the third question is kind of a homework question, because there is another approach where they try to identify influential data points using inference functions, and trying to articulate the difference between that and deletion diagnostics, I think, is an interesting thing to consider if you want to get into it, okay? So these are a couple of open questions that are worth looking into. All right, I think we are just in time really to come to the last bit of the slide deck. I hope in the process you got a good sense of the range of ideas in the area and what it encompasses. So let's take a step back and reflect on some of these and see what kind of directions might pop up in the future. Okay, so again, the reason we got started in this whole adventure is that machine learning landscape is being applied to a range of domains. Some of them are fairly safety critical and have massive societal implications. Things like security validation, things like surveillance, automated vehicles, and so on and so forth. So obviously we want to look at explainability, and it goes back to this kind of I don't know what you want to call it, whether you want to call it a threat or just a prediction that this is what us as a society will be tempted to do, is to try and automate as much as can be possible, even though there are clearly some concerns about automating some critical applications where, especially if you train the machine learning model on historical data, the biases get amplified, right? So obviously for these reasons, automations in some very many applications, in fact, should be taken up with the word of caution. Nonetheless, explanations and XAI can reveal information that becomes interesting, try to understand the relationship between the data and the decision boundary, understand things like bias and distribution drift and other things. But the area is not without its challenges, okay? I'll try and spend a few minutes talking about what kind of challenges are coming up. So one thing to note is that you remember I mentioned model agnostic versus model specific. And one of the challenges is that model agnostic methods are struggling to scale up. Okay, so this does mean that people can be hesitant to apply explanations if they find it very difficult to apply them. So for this reason, model agnostic techniques, it would be good to scale up machine learning explainability techniques anyway to address this. The other kind of thing is that, as you saw, there is not a clear guidance on automating explainability. If you think about it, in the last few years, we've seen quite a bit of work on automating machine learning, things like feature selection, hyperparameter tuning, so on and so forth. And it'd be good if you could have a similar kind of thing in in XAI. Certainly, for instance, you could think about approaches that automatically do feature importance, plot the dependence, train a surrogate model, train a simpler model, etc. So the whole range of things you could do, but it hasn't been done yet. So it would be an interesting direction to kind of provide this kind of service to machine learning models to make it easier to use explanations. Okay. We already saw this with counterfactuals, but more generally, explanations can be nonsensical, right? So the classic example is in images. If you have explanations that just refer to pixels, it can be hard to understand what they're really saying. So you need some kind of abstraction to understand how explanations work, okay? Going back to one of the earlier points in terms of having a pipeline for explainability, we need good interfaces for ML and explainability, right? You want, and some of these explanations need to be cohesive and easy to integrate with different machine learning systems. So, this is an area that needs to be, I mean, this is more on the engineering side, but nonetheless, it is an important problem for people to apply explainability broadly, okay? And finally, they are expensive. So this is something that we also need to consider. I mean, machine learning model training itself is expensive. So this adds another layer of complexity in terms of deploying explainability, okay? There are a couple of other issues. I think there are much softer issues, but nonetheless, they go back to the engineering. For instance, if you want to have a good perspective of what the model is doing, presumably you want to combine multiple different techniques and provide a kind of nice, a blackboard where you can see different perspectives of the model. So it would be nice to combine different techniques and present them. There is not much work on this, although people are trying to build hybrid models that combine different perspectives. There's also issues that they're vulnerable to adversarial attacks. So this could be an issue, obviously, in when people are actively trying to fool a system. And finally, there is also some issues that people are not really agreeing on a terminology in terms of different concepts that come up in the literature. But again, considering the fact that XAI, in the modern way we're looking at it, is a fairly new area, we expect that as things mature, people might try to ultimately converge on a common way to refer to concepts, right? So this is expected to happen, but not at the moment, okay? So we looked at the problems with machine learning, and we looked at some of the problems of XAI, okay? So, but we've also seen concrete ways in which XAI could be improved. We'll reflect on that once again. Before I get into that, let me quickly say that there have been some arguments that explanations and transparency do come with dangers, okay? The dangers have different dimensions. One very obvious dimension is that if you think about who is the explanation for, right? If you are trying to convince the user that the explanation is good for them, right? You could imagine the deployer tries to manipulate the explanation in a way that convinces the user. So in this regard, communication can become a form of manipulation. And if that's the case, we should be careful about accepting explanations given to us and the kind of actionable items that we can apply to in the regard that we may not be in full control of how the model really behaves, and only a small picture of it is presented to us to just appease us rather than really provide a concrete way for us to change the decision taken on our behalfs, okay? So that's one of the issues with it. And again, if you go back to one of the concerns at the start, that perhaps transparency is at odds with performance, then you might think, you might get into debates of the sort where you say, well, suppose I can deploy this system quickly. Should I spend the time making it transparent, or shall I go ahead and deploy it if it's expensive to make it transparent? And some might argue, well, yeah, go ahead and deploy it. We can worry about transparency later, but obviously this might mean other dangers come with it. And when we get behavior that is unexpected, we need a way to find who is accountable. And with the lack of explanations, it might be hard to do that, or which component is accountable for the mistake, right? So there are all sorts of debates you could get into when you try to think transparency is something that could potentially be expensive and not an obvious thing to add to a system. Again, with the research that is emerging, people are trying to address transparency as well as performance in the same light. But in the absence of that, there is space for such debates to occur and people to challenge these kinds of directions, right? They might say, let's just go for the best performing model and forget about transparency, and let's forget about explanations. Another aspect of explanations that we haven't quite focused on, and we have kind of just discussed it very informally, is that explanations ultimately, when you think about how they work in human communication, they're often contrastive and selective, right? If you ask me, why I'm giving a virtual tutorial now, the explanation that I have might be, I might offer the explanation as in comparison to another possibility. For instance, that physical conferences are yet still to come into place because of COVID and whatnot, and the explanation is targeted, right, based on the question you've asked. It wouldn't quite make sense for me to talk about the system I'm running a presentation on as an answer to your question. So they're selective and contrastive, and there isn't quite any systematic way to really achieve this, although there are efforts right now on trying to provide this flavor of this dimension to explanations at the moment, okay? And keep in mind as well that explanations really need to be targeted to a broad audience. So we need a way to abstract the details of the explanation depending on who is asking the explanation. So depending on the person asking the explanation, you might have to cater and potentially adapt the details of the explanation to the stakeholder, right? And that's, again, very challenging to do because we don't really have good definitions or frameworks to contextualize the amount of knowledge different groups have, and how to cater explanations to those groups in a systematic way, okay? So these are all explanations. So the challenges to explanations, and this brings me to what future directions could look like, right? One very attractive paradigm that's emerging right now is this idea that you can find a way to bridge the gap between low-level and high-level models. So this is kind of the paradigm of connecting of deep learning and symbolic paradigms, right? This is one area that's becoming very popular because deep learning models obviously pick up on low-level patterns, and symbolic models turn out to be usually interpretable. So a way to combine these two is an attractive direction. Combining the expressiveness combining the expressiveness of opaque models and the clear semantic of transparent models is another direction. Finding ways in which we can communicate the decision based on what the user is asking. So some kind of mental state modeling along with interactivity are obviously attractive directions in terms of where this area could go. One final thing that's really worth mentioning as well is the use of causality and causal analysis, as it allows you to clearly explicate what the main factors are in the decision and what the link is between them. So, causal analysis already turns out to be an important driver in areas like fairness and bias, and we should expect that, causal analysis might be fundamentally useful also in the area of XAI. One thing to note, however, is that there has been some discussion in explainability, at least in cognitive science, that causal attribution is just one facet of the overall explanation. So it's not a catch-all and solution to explanation, but it is an important ingredient, right? So there's a couple of different dimensions to keep in mind when we think about explanations and where they could go in the future. So this is kind of looking at a summary of all of these points. So we need explanation techniques that are able to combine and improve the pipeline and automate, whereas we also need to look at things like tailoring explanations for different stakeholders. We need to look at models that are transparent by design, so to speak, as well as have some notion of causality. That's essentially the takeaways that we have for this last bit. What sort of features are good to have for explanations? As I mentioned, they should be contrastive and selective in the least, right? Presumably much more, but they could start off from there. So here are some interesting directions for the future, and the kind of questions that permeate that. For instance, what are ways that we could do to automate XAI? As I discussed, in some context, you could potentially look at just like how ML has been automated by, pipelining, hyperparameter tuning, and data cleaning, and so on. You could imagine similar steps also done in the area of explainable AI. Okay. Another question for you to think about is ways we could address the dangers of transparency. And again, this is a kind of a multifaceted question, because you want to think about privacy. If in the process of explanation, you're revealing too much about the model to the person asking the explanation, then if the person asking the explanation is an adversary, perhaps they could use this to somehow for nefarious purposes, right? So there are challenges here that are cross-cutting, not just in AI, but potentially touching on miscommunication, deceit, privacy, so on and so forth. And it's not easy to really address all of these questions at once, but perhaps it's worth thinking about what kind of responses might be appropriate for such challenges, okay? And that's basically it from the tutorial. And I'm happy now to take questions. I'll stop the recording.